Hello guys, I'm a teacher Olimboka Studio Masame. Welcome to Olimboka Physics. The question below states that an object is placed at a certain distance from a convex mirror of focal length 20 cm. Find the distance of the object if the image obtained is magnified 4 times. Before calculating these questions, let us first use the Cartesian coordinate sign conventions to prove the mirror formula, especially for a convex mirror. This is our convex mirror, and we draw the Roy diagrams according to the Roy diagrams rules. And as you can see, the first rule, the second rule, the third rule, and the fourth rule. Okay, this is our height of our object. This is our image height. Image is from behind the mirror. That's why, and it is formed due to extended reflected backwards reflected rays. Therefore, the image formed here is not real, it's just a visual image. This is our poles, and this is our mirror plane that we use to easily get our geometrical diagram very accurately and for mathematical approximations. Okay, that's why we use this mirror plane here. This is our center P pole of this mirror. Okay. When we consider the triangle OPH and IPH for this visual image and for this object, in order to find the magnifications of this convex mirror under Cartesian coordinate sign convention. Okay, our tan theta here will be equal to opposite to its adjacent, as you can see, and our tan psi here will be equal to opposite to its respective adjacent. Okay. Oh, sorry, it's our tan theta here, sorry, not psi. Obviously, this is for it can give us the connection between the height of object and the height of image. Therefore, it will give us the magnifications, how much this image magnified comparing to the object. Okay, according to Cartesian conventions, as you can see the direction here, this is the pole, and all the displacement in horizontal, it is positive. Placement in vertical, about upwards, it is positive also, and the rest it is negative. This tan theta is equal to h naught divided by u, or u, as you can see here. U, it is a object distance OP, and the OH, it is h naught, and here IP, it is image distance as defined here. Okay, therefore and the IH, it is height of image, and therefore we have this expression as Roman 1. To relate with radius of curvature, okay, to relate with radius of curvature and the focal length, let us consider the triangle HCO, okay, C and O, and also a triangle H-I and C. All of these triangles, all of these opposites subtend an angle phi. Okay, as you can see here, a tan psi and a tan psi. Therefore, OH is H naught, HI dash is HI, and OC is a distance OC, the distance that is from PO, that is object distance, plus C, P, okay, plus PC, that OC, PC. This is the radius of curvature, okay, from the pole to the center of curvature. Okay, OC is equal to, and the IC, so this IC, IC is equal to our image distance minus our radius of curvature. Now is equal to our PC minus our PI. Okay, PC minus PI, as you can see here. Okay, and therefore now our tan psi for this case is equal, as you can see here, and our tan psi for this case is equal, as you can see here. We just substitute and we define these positions, as you can see here, as defined also here. Okay, and now our tan psi, as you can see here, and our tan psi, as you can see here, radius of curvature minus image distance. Okay, and here OP, it is object distance plus radius of curvature. Okay, for coordinate Cartesians, at this point, it is where we apply our coordinate Cartesian conventions, as you can see here, these directions. Now our tan psi is equal to tan psi for the small angle, the approximately is equal to the angle that is psi. Okay. Now we compare these two equations here, and after applying the coordinate cartesians, you can see that our h is positive, it's above principal axis, and the object distance is left negative. Our r is positive because it is in right. Okay, our h for image is positive because it is upright, and our radius of curvature, it is positive from 0, 0 here, and our image distance is positive as it is left from P. Okay, you are supposed now to divide with this in order to get the relationship of magnification. See, so as we compare with the equation number 1 here. Okay, after rearrange this in such a way that we have magnifications, we get to equation 2. Now we equate these two equations in such a way that this h object and image size will stand for magnifications, and this image and object displacement or positions will stand for magnification, but also will compare with this right side. After comparing this, then we cross multiplications. After cross multiplications, u must multiply with this one, and negative v must multiply with this one. Okay, after opening the bracket and rearranging the equations for the like terms, you find that this is twice uv, and you take r outside. Therefore, we divide with uv and we divide with r, so that the like terms will be on the same side. As you can see, we open this uv to each terms here above. Therefore, we'll have 1 divided by f, as we know, is equal to twice 2 divided by r is equal to, now we remain with 1 divided by v here, and remain with 1 divided by u. Okay, this is how we arrived into our general mirror formula by using a Cartesian coordinate sign convention for a convex mirror. Thanks for watching. Please like, share, comment. Don't forget to subscribe to this YouTube channel for more video like this one. Thank you.